Welcome to Math TV with Professor V. This is part 3 of the final exam review video for Calculus 1. So picking up where we left off, we're going to go over L'Hopital's rule, which you can use to evaluate limits which are of a specific indeterminate form, only of the type 0 over 0 or infinity over infinity. So here's the statement of L'Hopital's rule, just as a refresher. If the limit as x approaches a of f of x is 0 and limit as x approaches a of g of x is 0, or they both go to infinity, positive or negative, it's all good, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x, provided f and g are differentiable and all that good stuff. So either both f and g approach 0, or they both approach infinity or negative infinity. We don't care about the signs. Then you can take the derivative of the numerator and denominator separately. We're not doing quotient rule. We're doing illegal quotient rule. And then you can evaluate the limit from there. And you can continue the process multiple times if necessary, okay? But to be able to use L'Hopital's rule, we need an indeterminate form of the type 0 over 0 or infinity over infinity. Don't try to use it if you have any other type of limit. Now, these are two indeterminate forms. How many are there total? Do you know? There are 7. I like to think there's 7 indeterminate forms, like 7 deadly sins. Let's list them all. 0 over 0, that's 1. Infinity over infinity, there's another. Okay, we have infinity minus infinity. That's an indeterminate form. Why? Because they're basically competing. If one term's going to positive infinity and one's going to negative infinity, they don't cancel out. You have to investigate further. That's why it's indeterminate. It cannot be determined when it is in this form. So sometimes this will go to 0, sometimes it goes to positive infinity, sometimes negative infinity, sometimes a constant. I don't know. We need further investigation. Another kind of indeterminate form, infinity times 0. Think about why. One term is blowing up. The other one is shrinking to 0. I don't know which one's controlling the situation. The blowing up term, the 0 term. It cannot be determined when it's in this form. And then we have 3 indeterminate powers, okay? So we have 1 to the infinity, we have 0 to the 0, and we have infinity to the 0. When we say we have 1 to the infinity, it means the base is approaching 1, not that you actually have the number 1 being raised to the infinity. These are also indeterminate powers. You can use L'Hopital's rule when you have indeterminate forms of this type, but you just have to manipulate them to make them either 0 over 0 or infinity over infinity. Okay, so we'll look at some examples now. If you need a review, I have more in-depth lecture on L'Hopital's rule, of course. This is just to refresh you before your final exam. Okay, so use L'Hopital's rule to evaluate the limit. Before you even dream of doing such a thing, you have to make sure we have the correct indeterminate form, either type infinity over infinity or 0 over 0. So let's check. As x approaches 0, cosine of 9 times 0, that's cosine of just 0, minus 1, over, 0 squared. So cosine of 0, that's 1. Minus 1 over 0, so we have indeterminate form of the type 0 over 0. We're allowed to proceed and use L'Hopital's rule. And you want to indicate that you're doing so either by putting like L'H, that's the way I show my students. I know some instructors just put like a H with a circle. So, just do something to show, hey, I'm going to apply L'Hopital's rule right now. So we have the limit as x approaches 0. And now take the derivative of the numerator. So derivative of cosine 9x, we have to do the chain rule as well. Don't forget, it's going to be negative sine 9x times 9, right? So let me just write negative 9 sine 9x over derivative of x squared, which is 2x. Very good. So now let's see, can I evaluate the limit? So plug in 0 for x, that's -9 times sine of 0 over 2 times 0. Sine of 0 is 0, so 0 times -9 is 0 over 0. Oh, I don't have my limit yet, but thankfully I have an indeterminate form of the type 0 over 0. We can go ahead and apply L'Hopital's rule once more. So we have limit, x approaches 0. Let's take the derivative of sine 9x. It's going to be cosine 9x times another 9 because of the chain rule. So I'm going to have -81 cosine 9x in the numerator. Derivative of the denominator is going to be 2. Can I evaluate the limit now? Yes. Notice I just have a constant in the denominator. So this is -81. Cosine of 9 times 0 is just cosine of 0 over 2. We know cosine of 0 is 1, so this is -81 over 2. That's it. That was nice, right? I hope so. Now, it's a more spicy problem that's going to be useful. Here we have find the limit. They don't say to use L'Hopital's rule, but we're going to, okay? So we have the limit as x approaches infinity of 1 plus 2 over x to the 4th raised to the x. Now look what's happening here. As x goes to infinity, 2 over x to the 4th, that's approaching 0, right? A constant over infinity approaches 0. So the whole base, everything in the parentheses, is approaching 1. It's not equal to 1, right? It's not a constant. I have 1 plus 2 over x to the 4th, but as x gets large, it approaches 1. And then where's the exponent going? It's approaching infinity. So I have an indeterminate form of the type 1 to the infinity. Okay, now in order to use L'Hopital's rule, I have to somehow rewrite it so that it's of the type 0 over 0 or infinity over infinity. How do you do that? Well, when you have an indeterminate power, 1 to the infinity, 0 to the 0, or infinity to the 0, you're going to bust out a natural log. And there's a couple ways to write this up, but I'll just show you what I like to do. We're going to go ahead and let y equal the original expression whose limit we're trying to find. 1 plus 2 over x to the 4th raised to the x. Okay, now natural log of y is going to equal natural log of 1 plus 2 over x to the 4th to the x. Why am I busting out this natural log? Because I want to move the exponent to the front, and I can only do that. That's only a property of logarithms. You can't just go willy-nilly moving exponents if there's no log in the front. Okay, so this is now x times natural log of 1 plus 2 over x to the 4th. Okay, and that's what natural log of y is equal to. So I'm actually going to find the limit of natural log of the original expression. So let's say consider the limit as x goes to infinity of ln of y, which is going to be the limit as x goes to infinity of x times natural log of 1 plus 2 over x to the 4th. And currently, let's see what's going on. X to the infinity, this term here is approaching infinity. We already talked because 2 over x to the 4th is going to 0. This is going to 1. ln of 1 is going to 0. So now, have I made my life better? I have indeterminate form of the type infinity times 0. I need to make a fraction somehow. So if somebody needs to get flipped into the denominator, the easiest one to move usually is not the ln. Usually move this little guy. So if I'm going to flip x into the denominator, it's going to become 1 over x. Look, so I have limit x goes to infinity, natural log 1 plus 2 over x to the 4th over 1 over x. That's the same thing that I had written earlier. Dividing by 1 over x is the same thing as multiplying by the reciprocal x over 1, which is what I had earlier. But why am I doing this weird little maneuver? Because now I have an indeterminate form of the type 0 over, watch this, as x goes to infinity, 1 over x goes to 0, Oh, so now I have 0 over 0. That's the type of indeterminate form that we're allowed to apply L'Hopital's rule to. Do you see? Okay, so when you have a product, when you have an indeterminate product, oops, I wanted the laser pointer. When you have an indeterminate product, you take one of those terms, one of the factors, and you flip them down into the denominator. Usually it's not the ln, it's the other guy. Okay? Great. Now we're going to go ahead, apply L'Hopital's rule. We have to think carefully, though. This is a little more involved than the last problem because I've got some fancy chain rule here. Okay, so we've got the limit as x goes to infinity. Now look at the numerator. We know derivative of natural log of something is always 1 over the something. Just copy it down. No panic attacks. Times, and then now I have to multiply by the derivative of what's inside. Okay, well, what's inside is 1 plus 2x to the negative fourth. So if I take the derivative of 1 is 0, derivative of 2x to the negative fourth is going to be negative 8x to the negative fifth, right? You bring that exponent down, multiply, and subtract 1. That's over 1, technically, okay? Good, almost there. Now we need derivative of the denominator. That's x to the negative first, so derivative would be negative 1 over x squared. Okay, let's clean up. Let's clean up. It's a bit chaotic. These negatives cancel out, okay? And then let me show you how to clean this up in the best way possible. This is limit. X goes to infinity. I have 1 over 1 plus 2 over x to the fourth times 8 over x to the fifth, right? Isn't that true? Over 1 over x squared. Okay, I want you to notice something. If I distribute this x to the fifth, it's going to clean up a lot of what's going on in the denominator. So I have now the limit. X goes to infinity. 8 over x to the fifth plus, and then here if I distribute x to the fifth to 2 over x to the fourth, this will cancel entirely. I'm just going to have 1x left over, so plus 2x. Then I have, don't lose sight, divided by 1 over x squared. That's the same as multiplying by x squared over 1. Good? Ooh, okay, it's cleaning up, it's cleaning up, it's looking less chaotic. Now we have here limit x goes to infinity. You see, I can factor out one of the x's, then I have x to the fourth plus 2, right? So I can cancel this x with one of the ones up there. So then I just have 8x over x to the fourth plus 2. Okay, very good. Now let's see what's going on. As x goes to infinity, numerator's going to infinity, denominator's going to infinity. So we have indeterminate form of the type infinity over infinity. We could apply L'Hopital's rule again. Also, you used to do this limit before you knew L'Hopital's rule, and you would just divide by the highest power of x in the denominator. So you could also divide everybody by x to the fourth. It's up to you. So I'll just do L'Hopital's rule so we keep practicing. Derivative of the numerator is just 8, and then derivative of the denominator is 4x cubed. So as x goes to infinity, we just have 8 over infinity. A constant over infinity goes to 0. So finally, that's done. Now that's not the answer to the original problem, because remember, I just showed that the limit of the natural log of y as x goes to infinity is equal to 0. So what does that mean for our original problem? Well, if the limit as x goes to infinity of the natural log of y is 0, I have to take e and raise it to both sides, because I can pass that limit through. So this is the same as writing limit x goes to infinity of e to the natural log of y, and that would just give me back my original limit, right? And then that equals, on the right side, I have e to the 0, which is 1. So the final answer to whatever this limit is it's e to the 0, which is 1. Okay, so I don't know how picky your instructor is if they're going to make you write this whole blurb here, but basically whatever limit you get, what the result is here, just take e and raise it to that number, and that's the answer for the limit for the original problem without the natural log. Just think e and natural log, right? They're inverse functions, so they undo each other. So if you applied a natural log to the original expression when you found the limit, then to undo it, you have to take e, raise it to that. Okay? Good. I know that's a little confusing. Okay, now let's get into optimization. This is one of my favorite optimization problems. A rectangular sheet of perimeter 27 centimeters and dimensions x by y is to be rolled into a cylinder as shown in part A of the figure. So we've got this sheet of paper, basically, maybe it's something else, who cares? And then we're rolling it up into a cylinder. What values of x and y give the largest volume? Okay, so when doing optimization, always identify what's the quantity that you're trying to optimize, either maximize or minimize. You need a function of one variable expressing that quantity. So we're trying to maximize volume of this cylinder. So what's the formula for volume of a cylinder? At this point, you should start memorizing these. It shouldn't be like, oh my God, I've never seen this. Or if you haven't, now you have, and then memorize it. So next time it's not the first time. When you need volume of a right solid, right meaning height is perpendicular to the base, you just take area of the base times the height. So what's the base? The base is a circle. So circle's volume, or circle's area, excuse me, is pi r squared times the height, and I'm just going to already call this y, okay? Now, obviously, I need to get this down to a function of one variable, okay? I can't have r's and y's in there at the same time, because to find the maximum, I'm going to need to take a derivative, identify my critical values, etc., and you're not in multivariable calculus yet, so you don't take derivatives of functions of more than one variable. Okay, so let's look at the information that was given. I need to somehow eliminate some variables. Well, this part here that determines the circle, all right, that length is x. So x gets rolled up into the circle. Circumference of a circle is 2 pi r. So 2 pi r is equal to x. That means the radius is equal to x over 2 pi. So let me try to write everything as a function of x. That's the goal. I have pi times, instead of r, I'm going to write x over 2 pi squared. Now what about y? Right? We have to get rid of this. Well, I haven't used the fact that the perimeter is 27 centimeters. All the way around is 27 centimeters. So all the way around would be 2x plus 2y. That equals 27. I can solve for y in terms of x. 2y is 27 minus 2x. So y is 27 halves minus x. So 27 halves minus x. Have we done what we sought to achieve? I have v as a function of x alone. Perfect. Let's clean it up because I'm going to need to take a derivative in a minute. It's looking a little messy. So this is pi times x squared over 4 pi squared times 27 over 2 minus x. And then notice this pi cancels with one of the ones in the denominator. And I'm going to write v of x as follows. I'm going to take the constant out, so 1 over 4 pi. And then let's distribute x squared through to the other factor. So we'll have 27 over 2x squared minus x cubed. This will be the most friendly format we can write the function in to take the derivative. You'll see why right now. Okay, how are we doing? Good? All right, so we need the derivative. We're trying to optimize this function. So v prime of x. Remember, this 1 over 4 pi constants just come along for the ride on the derivative train. Derivative of 27 over 2x squared, You bring the 2 in the front, it's going to cancel with this 2. So I just have 27x to the first minus 3x squared. Great. So now we have to identify our critical values. That happens when the derivative equals 0 and when it doesn't exist. Okay, v prime of x equals 0 means all of this would equal 0. I can just junk the constant. It's not necessary. If I set it equal to 0 and divide both sides by 1 over 4 pi, it's not going to do a thing. So we have 27x minus 3x squared equals 0. I can factor out a 3x, and then I have 3x No, we're doing great. We have 9 minus x left over equals 0. Okay, that means either x is 0 or x is 9. V prime does not exist. That doesn't happen anywhere. Notice there's nowhere that this is undefined. It's a polynomial, in fact, so that's not necessary. Okay. I'm going to throw away x equals 0. That's not in the domain of the problem because they told me the perimeter is 27 centimeters, so it wouldn't make sense for x to be 0. We wouldn't even have a rectangle. We wouldn't even be making a cylinder, you know? Okay, so I suspect the only critical value of importance is x equals 9. That one should yield the max volume, but I need to confirm. I need to confirm that x equals 9 yields the max volume. And you can do that one of two ways. You can do the first derivative test and make your number line and test the sign of the first derivative on either side of 9. Or with a lot of optimization problems, I like to use the second derivative test. So v double prime of x, come over here, take another derivative. So 1 over 4 pi stays. Derivative of 27x to the first would just be 27 minus, this is going to be 6x, right? Good. Now, if I plug in 9, v double prime of 9, I have 1 over 4 pi times 27 minus 6 times 9, that's 54. And all that I really care is that this is negative. I don't even care what number it is. So the second derivative at 9 is negative. The second derivative tells us about the concavity of our function. So concavity of v of x. If it's negative, then that means it's concave down. And at the critical point, x equals 9, I know my derivative is equal to 0. So my tangent line is horizontal right there. And I can see clearly that x equals 9 yields a max because the concavity is down, right? Negative second derivative means concave down, which means that critical value is a max. So yes, it does. We're good to go. So for the final answer, I know x equals 9 yields the max volume. What did they want? The values of x and y. So x equals 9 centimeters. And then y equals 27 over 2 minus x, which is 9, which is 18 over 2, which is 9 over 2 centimeters. So we can summarize that more nicely. X is 9 centimeters and y is 9 over 2 centimeters. There's our final answer. Now this was a rather advanced level optimization problem, I'd say. It's not intermediate. I just wanted to do a nice review, but if you feel like, ooh, that was a bit much, I'm not so good at these, then I have a whole couple videos going through optimization, and it's all linked in the description. So just have at it. Have a little optimization party. Okay, shall we get into the next big idea of calculus? What is it? It's areas under curves. Oh, yes. So to start off this idea of finding the area under the curve, we begin by approximating it, typically using rectangles, okay? So here's the idea. Graph the function f of x that's given over the interval, partition the interval into 4 subintervals of equal length, and then add your sketch add to your sketch the rectangles associated with the Riemann sum, k equals 1 to 4, f of c sub k delta x sub k. Some books use i's instead of k's, whatever, it's all the same stuff. Using the indicated point in the kth subinterval for c sub k. So f of x is x squared minus 2. The interval is from 0 to 8, and we're using left-hand endpoints. Okay, so we're going to graph this function, x squared minus 2, on the interval from 0 to 8. Let's do that first, okay? So f of 0 would be negative 2. F of, let's just graph every 2 points. F of 2 would be 4 minus 2, that's 2. F of 4 would be 16 minus 2, so that's 14. F of 6 is 34. And f of 8 is 62. I mean, we know what a parabola looks like. We should. And it's just been shifted down 2 units, okay? So here it is in all its glory. Okay. Great. Now, partition the interval into 4 subintervals of equal length. So I want to know how wide, what's the length of each subinterval. We call that delta x. And to find delta x, you always take b minus a divided by n, where a and b are the endpoints of your interval, and n is the number of subintervals. Well, they just told me in the problem we have 4 subintervals, so that means n is 4. And I have a and b right here. Do you see them? There's a, there's b. Cool. So delta x equals, 8. I got too excited. B minus a, 8 minus 0 over 4, which equals 2. So that means the base of each rectangle that I'm going to draw right now should be 2. And if we're going from 0 to 8, let me indicate where that's going to be. 0 to 8. Then we're going to cut it up into 4 pieces. 2, 4, 6, right? Each base is 2. Okay, then this particular problem says use left-hand endpoints to determine the height for each rectangle. So that would be 0, 2, 4, and 6. So how does that exactly work? This can be a little confusing if you're new at it. So you come to, let's not make this so, I just want a pen. I want a gentle pen to draw this for you people. Okay, the first subinterval is from 0 to 2, but I'm using left endpoints. So the height of the rectangle is determined by the function value at 0. So you just draw a horizontal line segment for 2 units for however long delta x is, and then that's your rectangle. And then you can shade it in if you like. There's the first rectangle. Now, the area we would say is negative because the height of the rectangle goes in the negative y direction, okay? So this is signed area when we end up adding it all up. So you would take base times height. So the area of this guy would be delta x times the height, which is also negative 2. So this is negative 4. That's the area of that first little baby, okay? Then we come to the next subinterval. Again, we're using left endpoints. So I'm going to draw from that height at 2, not 4, a line segment of length 2 because that's what delta x is. And then we can color it in. Here's the next rectangle. Okay, very good. What's the area of this one? Area 2 would be base is 2, and height is also positive 2 now, so this is 4. Okay, next rectangle, use the left endpoint, right? 4 to 6, 4's on the left. So here's the height at 4, come across 2 units. There's the rectangle. Let's shade it in. And then let's determine the area of this rectangle, the third one. So area 3 is going to be base times height. Base is 2, height was 14, so that's 28. And then last one, use the left endpoint from 6 to 8. We're using 6. Here's my rectangle. Ooh, I went too far. Forgive me. I'll just scoot that over. Oh, heavens. No, no, no. Now I need a little partial eraser. Beautiful. Okay, what's the area of this rectangle? So the height is taken from 6, plugging it into the equation. 6 squared is 36 minus 2, that's 34. So area 4 is base, which is 2 times 34, so this is 68. And the problem asked us to evaluate the sum or the area of the 4 rectangles that we used to approximate the area under the curve here. Since we use left-hand endpoints, sometimes we'll call it L sub 4. So that would be the sum of -4 plus 4 plus 28 plus 68. These guys cancel, and that's just going to give us 96. Okay. Good. This is using left endpoints. Now, they didn't ask in this problem, but we also could set it up with right endpoints or midpoints. Should we try? Why not? Let's try. So let me erase the rectangles we just drew. Don't cry. All is well. And then we'll try again, and we'll switch things up, and we'll do it with right endpoints. Okay, and then maybe if we're feeling bold, we'll do midpoints. Depends what kind of a day this is. Okay, trying to gingerly erase all of this. Obviously there's error. We're going to talk about how to eliminate that in a moment. Okay, good. This was at -2. Okay, so say we're going to change things up and we're going to use right endpoints. Okay, great. That means on the first subinterval from 0 to 2, I'm going to take the right endpoint now and use that to determine the height of the rectangle. Oh, okay. So then that means the height is +2. So area 1 would be base times height, which is 4. Great. Now, using the right endpoint on the next subinterval, I'm going to choose whatever the function value is at 4. That determines the height of my rectangle. Okay. So area 2, what would area 2 be? Let's see. Base times height. Base is 2. Height is 14, so that's 28. Area 3, again. Now we're using the right endpoint. That's 34. Beautiful. Wow. Color it in. This is like the therapeutic part, right? Like I can unwind, pretend I'm in kindergarten again when the assignment of the day was coloring and you had to stay within the lines. At least that's what they did to me. I don't know. Area 3 is going to be base times height. So 2 times 34, which is 68. And then lastly, area 4. Remember, we're taking right endpoints. Woo. So that's determining the height of my rectangle. Where's that at? I believe 62, right? If I plug in x equals 8, 8 squared is 64, minus 2, 62. Yep, that seems about right. So then this is area 4. To compute the area of this rectangle, we do base times height. Base is delta x. Height is 62. So 2 times 62 is 124. Okay, if I add all 4 of these areas together, I'm going to get the R4 or right endpoint approximation for area under the curve. So it would be 4 plus 28 plus 68 plus 124. Let's see, 4 plus 28, that's 32. 32 plus 68 is 100, isn't it? Plus 124. Let me confirm. I'm freestyling right now. I hadn't intended to do the right endpoints, but let's do it. 4 plus 28 plus 68 plus 2 times 62, 224. Good. Now, obviously you can see this is an overestimate, right? There's all this excess area. And this is an underestimate. The true area underneath the curve, right, with no error is going to be between these two values. And don't think right endpoints always give you an overestimate, left endpoints always give you an under. It depends on the concavity of the curve, okay? If the graph was concave down, the situation would be reversed. What's even more precise is if we take midpoints of each interval, each subinterval to determine the height of the rectangle. So instead of using 0 or 2, if I use 1, 3, 5, and 7, I'll have even less error. So still 4 subintervals, right? But I'm using the midpoint of each to determine the height of the rectangle from the function. So let's try once again. I'm just going to erase all this, and we're going to do midpoints. And then there's a couple other ways you can approximate that you'll learn in Calc 2. You can use trapezoids and sometimes parabolas and whatnot, but usually this is enough. Okay, so now we're going to do midpoints. So for the first subinterval, I'm going to use the value at 1 to get the height. And you know what? Excuse me, if you plug in 1 squared minus 2 is -1. So like at 1, we should be at -1. A little lower than what I have drawn. At 1, we should be like down here, okay? I hope you can forgive me. So the first rectangle's height is going to be down there. So little, so low. Okay, that's at 1. So area 1, delta x is still 2, and then I'm going to have times f of 1, right? F of 1 squared minus 2 is -1, so 2 times -1, -2. Okay, next we're going to use the height of the rectangle based on the function value at 3. So come across here. Ooh, nice, right? So you have like a little overestimate, a little underestimate happening at the same time. That's why midpoint rule is more precise. See, this is a little extra, this is a little under. Usually it balances out nicely. What is area 2? So area 2 is base times height. That would be the function value at 3. So this is 2 times 3 squared, that's 9, minus 2 is 7. So that's going to be 14. 14. Okay. Area 3, we're going to take the height at 5, halfway between. Okay. Sorry for the wobbly rectangle. So let's see. The height at 5 squared minus 2, 25 minus 2, that's 23. So area 3 is going to be 2 times 23, so 46. And then last one is going to be at 7. You guys, I'm just eyeballing, so please bear with. Ooh, that was too far. Whatever, you get the gist. Let's plug in 7 into the function. 7 squared minus 2, that's 49. Minus 2, that's 47. So area 4, 2 times f of 7, 2 times 47, so that's 94. Okay, so now we have everything set up. We can figure out M4. That would be -2 plus 14 plus 46 plus 94. 46 and 94, that's 140. 140 plus 12, I want to say it's 152. But I'm going to confirm right now because it's important. 152. Good job. Good job, Professor V. Okay. Very nice. So you might be asked to do something like this. N could be different. It could be 6 or 8 or whatever. You could have more or less rectangles, but you should observe the more rectangles that you have, the better your approximation, the less error that there is. And so, of course, we want error to go to 0. We want no error. And then that drives the idea of taking a limit, making n approach infinity, and then we will get the exact area underneath the curve, right? If we have infinitely many subintervals and rectangles. So this is the next idea. And I wanted to work through an example with you guys. So find the formula and limit as requested. And we're asked to find for the function f of x equals 9 minus 2x squared. Take the limit of a Riemann sum, what we just did in the previous problem. Take the limit as n goes to infinity to calculate the area under the curve over 0 to 1. And these little formulas here off to the side are going to be necessary partway through the process. Okay, so here's the steps. We're going to set up the area, okay? And you do need to memorize. Let's think about how to get the area under the curve. It's the limit as n goes to infinity. We want no error of the sum of the areas that each of those little rectangles contained. So how many do we have? I have n many. I don't know. So I'm adding them up. That's why I have this sum. I equals 1 to n. Add up all your rectangles from 1 to n. The base of each is delta x, and the height is the function value at each subinterval. So we write f of x sub I times delta x. This represents the height of the rectangle at each subinterval. 1, 2, 3, 4. I don't know how many there are. We're going to go from 1 to n. So this is going to hit them all. This is height. This is base. Boom, boom. We add them all up, just like we did in the previous problem, right? We had 4. Now we have n many, and then we want no error, so we take the limit as n goes to infinity. This you should memorize. You should be able to write this down. No problem. So take the limit of a Riemann sum. We need to set up this whole sum and then take its limit. Okay, first thing you need to find, this is just go through the process methodically. First, find delta x. It's b minus a over n, right? They have to give you a and b. Here it is. A, B. Okay, so this is going to be 1 minus 0 over n, or 1 over n. Next, you need to compute what x sub I is. You can use right, left, or midpoint. Usually we use right. It's the easiest. So if you want to just memorize, it's a plus I delta x. That's how you find x sub I, using right hand approximation, right endpoint. So a in this case is 0, plus you just leave I in there, times 1 over n. So this is I over n. And then the third thing you should compute before you set everything up is f of x sub I. So you take your function f of x and you're going to substitute in x sub I for x. So it'll be 9 minus 2 times I over n squared. Okay. What does that give me? 9 minus 2i squared over n squared. That's f of x sub I. So now we're going to put everything together. So we have the area equals the limit as n goes to infinity of the sum I equals 1 to n. And I just always think base times height. Here's the height, 9 minus 2i squared over n squared, f of x sub I. Times, are you looking here in the formula? Times delta x. What was delta x? 1 over n. Don't forget that guy. A lot of the times students do, and then the limit goes to infinity or something. Okay, don't forget him. I'll draw the pay attention eyeballs. Pay attention. Okay, now to evaluate this limit, let's distribute through. So we have the limit as n goes to infinity of the sum I equals 1 to n. Distribute this. That's what I mean. 9 over n minus 2i squared over n cubed. Okay. Now, a couple different ways you can really break it down and distribute the sum if you want. So this is the limit as n goes to infinity. I could write this as the sum I equals 1 to n, 9 over n, minus the sum I equals 1 to n, 2i squared over n cubed. Okay, and then now this is where we're gonna go back to those little formulas I had up above. I'm summing from I equals 1 to n, 9 over n. No i's appear in the expression here. That's equivalent to summing up a constant from I equals 1 to n. There's no i's here. So in order to evaluate that sum, you just take whatever expression is here and multiply by n. So I can rewrite this as just 9 over n, that's my c, that's my constant, times n. Okay, that part all right? Minus, now look here, I have 2 over n cubed, okay, that's basically a constant, times I squared. So come up here, the sum, I equals 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6. Either your instructor is going to have you memorize these summation formulas or they'll give it to you. So I can basically replace the sigma and the I squared with this entire expression. I'm going to go ahead and do that. Get rid of the I squared and get rid of the sigma. Get rid of the I squared and get rid of the sigma. Okay, all the stuff in pink goes away. And I'm going to replace it with n times n plus 1 times 2n plus 1 over 6. And then what happens to the blue terms, the 2 over n cubed, they just hang out. Those are constants. Nothing happens. Okay? Whew, good. The worst is over. Now we just take this limit. Pretend like it's a fresh problem. These n's cancel. Can I cancel some more stuff? I can cancel one n here, make this an n squared. I can cancel the 2, and now this is a 3. So let's see, we've got the limit as n goes to infinity. This is 9 minus, I have n plus 1 over 2n plus 1 over 3n squared, right? That's everything that didn't cancel out. Good. I'm going to need another piece of paper. Hold on. I'm running out of space. Let's get this back on track. So now we have the limit as n approaches infinity. Best way to evaluate this limit, multiply out the numerator. So FOIL it out. It's going to be 2n squared plus n plus 2n. So that's plus 3n plus 1 over 3n squared. And then I can split that 3n squared under each term in the numerator separately. Watch. So this is going to be 9 minus 2n squared over 3n squared minus the negative distributes, right? 3n over 3n squared minus 1 over 3n squared. And then clean up a wee bit more. I'm not skipping any steps so we don't lose any of you. 9 minus, this is 2/3 minus, well, the 3's cancel, so I could just write this as 1 over n, right? Minus 1 over 3n squared. And then here's the fun part. N goes to infinity, so this guy's going to go to 0. This guy's going to go to 0. And the other two terms are just constants. So we just have 9 minus 2/3. So that's 27 over 3 minus 2 over 3, which is 25 over 3. All right. And then assuming we're doing this as, you know, a final exam problem, you could check using fundamental theorem of calculus, part 2, okay, to check that you did everything correctly by just evaluating that definite integral from 0 to 1 of 9 minus 2x squared dx. I know we haven't talked about this yet, but if you're watching this for review purposes, you should know how to do this. So anti-differentiate 9x minus 2/3 x cubed from 0 to 1. Yep, that's 9 minus 2/3 minus 0, which gives us the exact same result. So you can always check your work. If this appears on a test or something and you're nervous because it's a little bit of a lengthy process, go ahead and check your work, okay? Nothing wrong with that. All right, so let's continue that idea of finding areas under curves. But now, instead of computing a Riemann sum and taking its limit, we're going to use a graphical approach. So the directions state graph the integrand. This is the integrand. And use areas to evaluate the integral. So the integrand, the function whose area we're trying to figure out under its curve is f of x equals rad 49 minus x squared. Okay? And we want to figure out the area under this curve from -7 to 7, since those are our limits of integration. Now, do you recognize what this represents the graph of? If not, it's okay. F of x is the same as, we can just write y equals rad 49 minus x squared. I'll square both sides, so now I have y squared equals 49 minus x squared. And then let me put all the variables on the left. X squared plus y squared equals 49, right? Do you recognize it a little bit better now? If not, it's okay. I'll refresh your memory. This is a circle centered at the origin with radius 7. Okay, so standard form equation of a circle is x minus h squared plus y minus k squared equals r squared. And the center is at hk and the radius is r. All right, so let's graph that. And then we're going to see things will unfurl nicely. The problem is set up in a specific way that we're going to be able to compute this area with ease. Okay, so center is at 0, 0. Radius is 7. Let me actually put the circle in and then I'll label so it comes out perfect. I'll just say, you know what? 7 is actually now right here. Here is 7. Here is -7. -7. Now be careful. We're not actually dealing with the whole circle. The whole circle would be had we been given this equation. But as you can see, this circle is not a function. No, it is not. And when we were originally given our integrand, we only had the positive radical. That means we're only dealing with the upper half of the circle. This portion is not here since we were given the positive radical. So we just have actually the upper half of a circle whose radius is 7 centered at the origin. Okay, so now look back at the integral. It represents the area under this semicircle from -7 to 7 that's bounded by this curve as well as the x-axis. Okay, so let's shade in the area represented by the integral from -7 to 7. Could you compute that directly without having to use any calculus or anything fancy? Yeah, I mean, it's just the area of half a circle, right? And we know area of a circle is pi r squared, so it's going to be 1/2 pi r squared. And we just established the radius of this semicircle is 7. So this is 49 pi over 2. All right, see, no big deal. Now, here's the thing. These limits have to be set up just so that you could easily cut up the area of the circle. Say, for example, this -7 was -6 instead. Well, then we'd be stuck because we don't have a nice formula that's going to remove that fraction of the circle from the problem. Alternatively, though, if this had been maybe like a 0 instead of a -7, that's fine. Then we would have had 1/4 of the circle. So 1/4 times pi times 7 squared, so 49 pi over 4. Because going from 0 to 7 would mean we just have that portion. Okay, so the limits have to be set up so specifically in order for you to use geometry and areas in this way. All right, other things that you might have to graph, just different sets of lines, geometric shapes. If this sort of a problem appears on your exam, be prepared, to just do formula for areas of rectangles, triangles, excuse me, and then semicircles or circle. There's not really much else you can do at this point. Okay, very good. Now let's just go ahead and evaluate definite integrals not graphing, just using the fundamental theorem of calculus. So here it says, evaluate the definite integral from 1 to 4 of t plus 1 over t quantity squared dt. So I'm not going to graph it. I'm not going to do a Riemann sum. I'm going to use fundamental theorem of calc part 2. If you forgot it, let's scroll back up. You know what? I think it's lower down. Just kidding. Hold on. Here we go. Here's our fundamental theorem of calculus. Part 2 tells us definite integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where the derivative of this capital F gives you back your integrand, your lowercase f of x. So capital F is an antiderivative of lowercase f of x. So that's what we're going to do right now. Fundamental theorem part 2. All right, so we have an integrand from 1 to 4, and I'm actually going to multiply out t times 1 plus t. So if you need to FOIL it out like this, feel free. I'm just going to do it quickly. So it's going to be t squared plus t times 1 over t is just 1. I have 2 of those. Plus, then I have 1 over t squared, which I'm going to write as t to the negative second. Why am I doing that? Because I'm getting ready to take an antiderivative, right? So it's easier for me if I have all of my exponents right here, not written as 1 over t squared, in order for me to do that. Okay, so when you're antidifferentiating, you add 1 to the exponent, divide by the new exponent. So if I add 1 to the exponent, it would be, yes, t cubed. And then I divide by the new exponent, so this would be a 1/3. Or you could put it all over 3. It's really up to you, okay? Plus, if there is no variable, then you just add 1. It's as if there's t to the 0, so you're going to make it t to the first, okay? So anytime there's a constant, you just add a variable. And then t to the negative second. Let's think. If you add 1, you'll have t to the negative first. And then if I divide by the new exponent, I'm dividing by a negative. So I'll just put a minus sign out front there. And then now we have to evaluate everything from 1 to 4. Okay, you plug in the upper limit first. So I'm plugging in 4. So I have 1/3 times 4 cubed plus 2 times 4 minus 4 to the negative first is 1/4. Minus, now I'm going to plug in 1. 1/3 plus 2 minus 1. Okay, 4 cubed, that's 64. So we've got 64 over 3 plus 8 minus 1/4 minus 1/3. What is this? Positive 1 minus 1. Okay, so 64 over 3, I'm just going to do these guys together, minus 1 over 3, that's 63 over 3. 63 over 3 is 21, plus 8 minus 1, so plus 7, minus 1/4, so it's 28 minus 1/4. 28 times 4, let me get a common denominator, that's 112 over 4 minus a fourth, so 111 over 4. All right, very good. Let us move on with our lives. Enough of that. So now we're going to look at more of the fundamental theorem of calculus, okay? We're going to consider part 1. Which introduces the idea that a derivative and an integral undo one another. Derivative, antiderivative in a way. Okay, so part 1 tells us if we take the derivative with respect to x of an integral, and it's not our normal definite integral. The lower limit needs to be a constant. It doesn't matter what it is. And then the upper limit is x, a variable. And we're differentiating with respect to that variable. And then here's our integrand, f of t dt. So these variables here in the integrand are not the same as the variable in the upper limit. They can't be the same. Otherwise, it's not well defined. Anyways, part 1 tells us that essentially this derivative and this integral undo one another. And so the x simply gets substituted into f. And you don't need to actually do anything to the function. You see, I'm not switching it to capital F. I'm not finding its antiderivative. This would have me do just that. But then if you take a derivative again, you're undoing what you just did. So simply plug in the upper limit. If this upper limit is not a variable, we have to do some things to make it so. And if it's anything more involved than x, then we have to follow our differentiation rules, because what we're doing is taking a derivative and apply the chain rule. So you'll see what I'm talking about right now. Here we go. So find the derivative. So dy dx, we're differentiating with respect to x. Why do I say x? Because that's the variable in the upper limit. Pay no mind to that one. So derivative with respect to x, let me write that on both sides. Applying the fundamental theorem of calc, part 1, means I do precisely the following. I'm going to take x and replace it everywhere I see t in the integrand. So the result is square root of 8x plus 7. Yes, that's literally all you do. Does it feel peculiar? That's okay. This is like a warm-up problem. Let's try another. Take the derivative with respect to t, okay, of the integral from 0 to sine t. So far things are good. This is not plain old t, but it is a function of t, and that's what I'm differentiating with respect to. So everything looks good. And then see how we have different variables here in the integrand. U squared, 1 over 4 minus u squared du. So all I'm going to do is just plug in sine of t for u, so 4 minus sine squared t. And then since this upper limit was not just plain t, right? It's sine of t. And what am I doing? I'm taking a derivative. I need to use my differentiation rules, in this case apply the chain rule, and multiply by the derivative of this upper limit of sine t. So derivative would be cosine t, positive, yeah. And then I was hoping there was some clever way to clean this up, but there isn't. So there you go. You're just going to put the cosine t in the numerator nicely like this, okay? And then we're done. All right, here's another one. Integral x to the 4th to 0 cosine rad t dt. Now, don't forget the lower limit needs to be a constant, upper limit needs to be the variable. So what do we do if it's not set up properly? You can flip the limits, right? And when we do that, it changes the sign of our integral. So we have negative 0 to x to the 4th cosine rad t dt. Okay, now let's go ahead, differentiate with respect to x. So derivative with respect to x of negative 0 to x to the 4th cosine rad t dt. Go ahead, substitute in x to the 4th for t. Keep the negative. So we have cosine rad x to the 4th, and then use the chain rule, multiply by the derivative of x to the 4th. What would it be? 4x cubed. Very good. And then notice rad x to the 4th. Ooh, I wanted a highlighter. Come to me, highlighter. Square root of x to the 4th, we can simplify and just make it x squared. So let me put that all together. Negative 4x cubed, and then we have cosine of x squared, like that. Very good. All right. Now we're going to learn a technique of integration called U substitution. I'm just going to jump right in, assume that you've seen it and you've practiced it, so now it's time to get professional at it. So we have an indefinite integral this time. See, no limits of integration. That means we're going to have to put plus c at the end. Okay, plus c when there's no limits. X dx over 7x squared plus 3 to the 5th. Okay. So typically you use U substitution when you have a composition of functions. You have a function sitting inside another one. And I want to let 7x squared plus 3 be u. All of it, the plus 3 as well. Why do I want to do that? My eye is instantly drawn because I know the derivative of anything squared is going to involve x to the 1st power. And I see I have x to the 1st in the numerator, so it should work out nicely. If you have a constant, always throw that in there when you're picking u, because the derivative of a constant is just going to be 0, so it simplifies things immensely. So now I'm going to take the derivative of both sides. When you're starting off, you might need to write du dx equals 14x, and then you move the dx over, so you have du equals 14x dx. Okay, I'm not going to write it like that again. Usually I just go straight from here to this step. All right. Now, I want this right-hand side to match what I have in my integral. So let's come back to the integral, take a peek. All I have is x dx. So I want to get the x dx all by itself on the right. So to do that, let's divide both sides by 14. So 1/14 du equals x dx. And now I'm ready to make my change of variables, okay? So in the numerator, instead of x dx, I have 1/14 du over, and all of this mess, 7x squared plus 3 is u raised to the 5th. Do you see? Take a second, marinate on it. And now you should not ever write your integral half in x's, half in u's. Okay, that's not well defined, and you're not in multivariable calculus yet. So when you're going to do a u sub, you need to change it all from x's to u's in one clean step. Okay? Yes. Now let's proceed. So anytime I have an extra constant like this, oof, I like to take it outside so it's not bothering me. It's out of the way. So 1/14. And then I know I'm going to have to take an antiderivative. So that u to the 5th in the bottom, no, I need it as u to the negative 5th. Okay? What's our rule? Add 1 to the exponent, divide by the new exponent. So add 1. Now I'm going to have u to the negative 4th, divide by the new exponent. Divide by negative 4, that's the same as multiplying by negative 1/4. And then don't forget, plus c. Plus c because this represents a family of antiderivatives, yes, that could satisfy or be the antiderivative for the integrand. Okay, very good. Now we have to clean up a wee bit more. Negative 1 over 14 times 4, that's negative 1 over 56. And then let's return to the original variable. Instead of u, I'm going to go back to 7x squared plus 3 to the negative 4th plus c. And that one's done. Yay! Shall we try another? Oh yes, these are so fun, I think. Hopefully you enjoy doing some integrals. Indefinite integral 9x squared times the 4th root of 10 plus 2x cubed. Ooh. Okay, so notice what's underneath the radical involves x cubed. And you see how what's sitting outside is just x squared? Then that leads me to believe what's underneath the radical is a good choice for you. Okay? Whatever's kind of in the parentheses, under the radical, you could see that it's clearly a composition. All right, let's proceed. So I'm going to say let's let u equal 10 plus 2x cubed, and then du would be 6x squared dx. I already moved the dx over. You're going to do this so much in your life, we got to get the ball rolling. Okay, so now look back at this integral. Let's take the 9 out, okay? Oof. Could I have written it any uglier? 9, and then x squared 4th root of 10 plus 2x cubed dx. I always tell my students, draw your kidney bean, basically what you suspect du needs to become. See, x squared dx. There it is, x squared dx. So I'm going to divide by 6 on both sides. So 1/6 du is x squared dx. So the kidney bean gets replaced with 1/6 du. So 9 integral 1/6 du. I'll write it like that for now. And then we have 4th root of 10 plus 2x cubed. Who's that? That's u. Okay, now let's get a little more slick. Why do we have this disgusting 1/6 here? No. Put it outside with the 9. And then this differential needs to always be all the way on the right, okay? So 9 over 6, that's 3/2. Lovely. 4th root of u, no, we're not leaving it like that. That's going to be u to the 1/4 du. And see, I already moved the du out there. Okay, beautiful. Now we're ready to roll. Look at the exponent. Add 1 to it. 1/4 plus 1, that's 5/4. Divide by the new exponent, so multiply by 4/5. Don't forget your plus c. And then let's see, can we clean up? Yes, cancel the 2. This is a 2 now. So I have 6/5. Instead of u, I'm going to write 10 plus 2x cubed to the 5/4 plus c. That's it. Voila. And you know, you always could check your work. Just take the derivative of what you have here, and you should get back the integrand. Otherwise, you did something wrong. Okay. Let's look at some more u subs. Here we have 1/t² times sine of 2/t plus 3. Now, even if it's not obvious to you right away what to let u be, when you see a composition, when you see a bunch of stuff in parentheses, good chance that's what you should let u be. So let's see. Let u be 2/t plus 3, which is 2t to the negative first plus 3, right? So let me find du. Take the derivative of 2t to the negative first. It's going to be negative 2t to the negative second. Derivative of 3 is 0, and then I have dt. Oh, now look. I have t to the negative second over here, and I'm so excited because that's the same as 1/t², isn't it? So let me just get rid of this negative 2. So negative 1/2 du equals, instead of t to the negative second, I'll rewrite it as 1/t² just to make it super obvious for you guys. So look, here we go. Here's 1/t² dt. That's exactly what's right here. And that I will replace with negative 1/2 du. So look, this integral is going to transform beautifully. I'm going to put the negative 1/2 outside. Then you just have sine of u du. Take a second, marinate on what just happened. Okay, so this 1/t² dt, right here, 1/t² dt is negative 1/2 du. I already put the du on the right, and I put the negative 1/2 outside. And then sine of 2/t plus 3, that's sine of u. Bam. Doesn't this look like a friendly little integral? So whose derivative did we take to get sine of u? Remember, derivative of cosine u would be negative sine u. Oh, there's already a negative. So if we're going backwards, this is just positive 1/2 cosine u plus c. And then go back to the original variable. 1/2 cosine of u was 2/t plus 3 plus c. Don't lose points by forgetting the plus c, okay? I'm warning you. If you're going to make a mistake, make a original one. Don't make a very cliched one that you were warned about. Okay, use the substitution formula to evaluate the integral. That's a weird way of saying use u sub. Okay, so we have definite integral this time. 0 to pi, 1 plus cosine of 5t² times sine of 5t dt. So, any guesses what we should let u equal? Yes, everything in the parentheses here. So we're going to let u equal 1 plus cosine 5t. And then take the derivative. Du would be, so derivative of 1 is 0. Derivative of cosine 5t would be negative sine 5t. But then don't forget the chain rule, times 5. So this is negative 5 sine 5t dt. Do you see that in the integral somewhere? Yes, it's right here, sine 5t dt. Oh, good, good. So that means negative 1/5 du is sine 5t dt. And we're almost ready to continue. So 1 plus cosine 5t, all of this is just u. So we're going to have u squared. Cool. Then we have this sine 5t dt, and it's negative 1/5 du. So du, negative 1/5. Then we need to change our limits. right here. These limits belong to the original variable that was in our integral, t. 0 and pi belong to t. I need my new limits for u. So let's go ahead and figure out what they are. I'm just going to plug them in for t. So u of 0, the lower limit, would be 1 plus cosine of 5 times 0. That's still cosine of 0, which is 1. So 1 plus 1, this is 2. My new lower limit is 2. And then u of pi is 1 plus cosine of 5 pi. Cosine of 5 pi is just coterminal with cosine of pi, which is negative 1, so this is 0. Okay? You need to change your limits immediately. If you start with a definite integral, every single step along the way in the problem, you need to include the limits of integration. Don't leave these in terms of t. These limits need to match the variable that's here in the integral. All right? Good. Now, a couple things we can do to make the rest of the problem easier. I'm going to flip the limits, okay, and then make it positive. So I can get rid of that negative sign now if I go from 0 to 2 instead. U squared du. Isn't that nice? I think so. And then now we're ready to anti-differentiate. So add 1 to the exponent. It's going to become u cubed. Divided by 3 is multiplying by 1/3. And then we'll evaluate from 0 to 2. Okay, we have 1/15. Just leave the constant outside, please. So 2 cubed minus 0 cubed. You don't need to keep bringing the constant every time you plug in upper limit minus lower limit if it's outside like that, okay? It'll make life so much easier. This is 1/15 times 8 over 0, so this is 8 over 15, and we are done. No, don't put plus c. Don't put plus c. When you have a definite integral with limits like this, there's no plus c. Your answer is a number, okay? Represents area under the curve of the integrand. But, you know, we don't always care about it as an area, but I'm just saying, don't put plus c. Okay, and I think, you guys, this is the last one. Wow. No, I'm lying. There's quite a few more. This is the last integral. So 0 to natural log of rad 3 over 4. And this is 4e to the 4x dx over 1 plus e to the 8x. Okay, I did want to clarify that this upper limit is it's missing a set of parentheses. It's natural log of rad 3 all divided by 4. So let me rewrite this. 0 to ln of rad 3 over 4. And then 4e to the 4x dx over, I'm going to help inspire you. Are you ready? E to the 4x squared. Oh, okay. So this one's a little spicy. I'm going to go ahead and let u be e to the 4x. So if u is e to the 4x, du would be 4e to the 4x dx. And oh my stars, here it is. That's my du. Wow. The other thing is, we need to change our limits of integration. So right now, let me just fill in what we have. Du in the numerator over 1 plus u squared. And you might be saying to yourself, I would have never thought to do that. I know. It's just, I've done so many problems that it just screams at me now. Like, oh, this is the substitution to make. So you too can get there. Just keep practicing. The more you add to your repertoire of successfully solved integrals, the more equipped you are when you see another one to draw upon that repertoire and say, aha, this resembles that scenario. Now I know how to proceed. It's pattern recognition. Okay, now the limits. So lower limit is 0. That should be straightforward. U of 0 is e to the 4 times 0, so that's 1. Upper limit, u of, and this is ln rad 3 all over 4, so it's e to the 4 times ln rad 3 over 4. These cancel. E to the ln of rad 3 is just rad 3. So new lower limit 1, new upper limit rad 3. Okay, from here you should recognize the antiderivative. If you forgot, I will remind you. Do you remember the derivative of tan inverse of x? It's 1 over 1 plus x squared. So that means antiderivative of 1 over 1 plus x squared dx is tan inverse of x plus c. Well, that's what we have right here. 1 over 1 plus u squared instead of x squared. That's fine, no big deal. So antiderivative is tan inverse of u. No, I'm not going to put plus c because this time I have limits from 1 to rad 3. Ooh, do you know your trig? So tan inverse of rad 3 minus tan inverse of 1. So when is tangent rad 3? I just think when is sine rad 3 over 2 and cosine 1/2? That's at pi over 3. Tan inverse of 1, that's at pi over 4. Common denominators, pi over, it's going to be 12. So this is 4 pi over 12 minus 3 pi over 12, which is 1 pi over 12. I love this problem. I've put it on my final many times. Okay, now we're going to revisit particle motion since we know how to take antiderivatives. We can answer some interesting things. So solve the problem. At time t, the position of a body moving along the s-axis is given as follows. So s of t is t cubed minus 9t squared plus 24t. Find the body's acceleration each time the velocity is 0. So if I take one derivative of my position function, I now have the velocity function. So what would that be? Yes, 3t squared minus 18t plus 24. And then while we're at it, let's go ahead and get the acceleration function. That's the second derivative of the position function, which is also v prime of t. This is a of t. He has so many names. Look at that. Derivative again would be 6t minus 18, right? So the problem is saying find the body's acceleration. Okay, find this each time the velocity is 0. So I need to set the velocity function equal to 0 first. So let me do that down here. So 3t squared minus 18t plus 24 is 0. I feel like it's going to factor, but let's divide by 3 first. So t squared minus 6t plus 4 is 0. Oh, plus 8. What am I doing? It's rather early in the morning, but that's no excuse. Okay. So yes, this factors beautifully. T minus 4 times t minus 2 equals 0. So velocity is 0 at 4 seconds and 2 seconds. I'm assuming we're talking seconds. They didn't say. Okay. I'll say time is in seconds. Now we need the acceleration at each of these times. So I want the acceleration at 2 seconds and at 4 seconds. So at 2 seconds, it's going to be 6 times 2 minus 18. That's 12 minus 18, so negative 6. Units on acceleration are meters per second squared. They told me meters right here. And then acceleration at 4 seconds, I'm plugging in just right here. 6 times 4 minus 18. 24 minus 18, that's positive 6 meters per second squared. So don't forget your units, especially if the problem mentions what they are, then it's part of the solution, okay? All right, this you could have done before learning antiderivatives, but now I just wanted to refresh your memory on particle motion. We're gonna go the other way, okay? What do I mean? You'll see. Sorry, I needed a sip of coffee. Okay, given the acceleration, initial velocity, and initial position of a body moving along a coordinate line at time t, find the body's position at time t. So what they want is the position function. They want s of t. And to kick it off, they gave me a of t. A of t is sine 5t plus 12. Okay, well, to get the velocity function, I mean, I have to go along that route. So I'm starting with acceleration. To get to position function, we have to take two antiderivatives, right? when we go from position function to acceleration, we take two derivatives. So to go backwards, we have to undo it twice. So velocity is going to be, you can write out an integral if you want, sine 5t plus 12 dt. Velocity is going to be antiderivative of acceleration. So do you need to do a u sub for this? Probably. Let's talk about it. So we have antiderivative of, let's just look at the sine 5t, okay? If we let u be 5t, du would be 5 dt. So 1/5 du is dt. So then now we have 1/5 integral sine of u du. Okay, take the antiderivative. It's going to be negative cosine u. So this is negative 1/5 cosine of u plus c. And then when you go back to your original variable, we have negative 1/5 cosine of 5t plus c. Okay. Now I want you to notice something that's going to save you so much time. Okay. Antiderivative of sine 5t is negative cosine 5t. And then I divided by 5, right? Because notice I have that constant 5 in front of t. And we're basically undoing when we multiply by 5 and take the derivative using the chain rule. Because if you think about it, when you take the derivative of cosine 5t, right, you would get negative 5 sine 5t. But if you look here, there's no 5, so that's why we have to divide by it. All right, so if you want, you can skip this whole u sub. You certainly can. If you see that all there is a constant in front of the variable like this, just divide by whatever that constant is. If that stresses you out, then do a u sub. I'm not stressed, so I'm just going to proceed. This is negative 1/5 cosine 5t plus antiderivative of 12. It's a constant, so just add the variable plus c. Now I do want to solve for c here before I keep going, and they told me v of 0, so the velocity at 0 seconds is negative 1/5. That's to help me solve for c. So let's go ahead and do that. So v of 0 equals, I'm going to plug it in right here. So this is negative 1/5 times cosine of 5 times 0 plus 12 times 0 plus c. And this equals, they told me, negative 1/5. So negative 1/5 cosine of 0 is 1 plus c equals negative 1/5. So that means c is 0. Okay, so v of t is just negative 1/5 cosine of 5t plus 12t plus 0. All right, we are almost there. Now we need one more antiderivative to get the position function. So s of t is going to be antiderivative. You know what, let me just properly add a page. This is feeling chaotic to me. Okay, so s of t, scoot down here, is going to be antiderivative of the velocity function. All right, let's write it out nicely. Negative 1/5 cosine 5t plus 12t. Don't forget, you got to put a dt. You need that differential there. Again, you could use sub, or we could just say, hey, I'm going to divide by 5. That's it. So antiderivative of cosine 5t is going to be just 1/5 sine 5t. And I already have another negative 1/5 out there. So you leave that one, you add another 1/5, and then we have sine 5t. Antiderivative of 12t, well, you're going to add 1 to the exponent, so it's going to become t squared, and then you divide by 2. So 12 over 2t squared plus, I'm not going to put c, I already used c, so let's say d. Okay, clean it up a wee bit. S of t is negative 1 over 25 sine 5t plus 6t squared plus d. Can I solve for d? What did they tell me? S of 0 equals 10. Oh, perfect. So S of 0 is negative 1 over 25 times sine of 0 plus 6 times 0 plus d, that equals 10. I think everybody's 0, right? This is 0, this is 0, so d is 10. And then at long last, here's our position function. S of t is negative 1 over 25 sine 5t plus 6t squared plus 10. Et voila. Beautiful. Beautiful. Okay, last idea I want to go over is total distance traveled versus displacement. Okay, so here the problem says, given the acceleration a of t equals 2t plus 3, and initial velocity v of 0 equals negative 4 for t between 0 and 10, find the displacement and total distance traveled by the particle over the given interval. Now, the formula for displacement and total distance traveled depends on which function you're working with. When you first learned the concept, you worked with the position function. Can I get the position function based on what they gave me? They gave me acceleration, which is two derivatives of the position function. And they gave me an initial velocity. So I can anti-differentiate this once and get the velocity function, but I can't do it one more time and get the position function because they didn't tell me anything about the initial position. So I can't use that very first definition I learned about displacement and total distance traveled. Instead, I'm only going to be working with the velocity function. So definition for displacement when you're working with velocity would be definite integral from a to b of v of t dt. When you're trying to find the total distance traveled, the only difference is you still integrate from a to b, but you need to take the absolute value of the velocity function. Why is that? Well, remember, total distance traveled will be different than displacement if the particle changes direction. And so the velocity will indicate the direction of the particle. Particle's moving in the positive direction when velocity is positive, and it's moving in the negative direction when velocity is negative. So if we take the absolute value of the velocity function, then that ensures that when the particle is moving in the positive or negative direction, they don't undo each other, and we truly capture the total distance traveled, okay? The way you compute it is a little different when you have the position function. That's the first way you learned, like I said, which we're not going to do here because we can't get the position function. So to start things off, here's acceleration. I need velocity, right, for both parts. I need velocity. So let's go ahead and get it. So v of t is going to be antiderivative of 2t plus 3. Antiderivative of 2t, what's that? Yeah, t squared, and then you're going to divide by 2, so the 2 cancels. So just t squared plus antiderivative of 3 is 3t, and then put plus c. Now I need to find this c, and I can do it by coming right here. V of 0 is negative 4. So v of 0 would be 0 squared plus 3 times 0 plus c. It's negative 4. So at long last, we can say v of t is t squared plus 3t minus 4. Beautiful. All right, now we can answer part A and give the displacement. So displacement is going to be, let me write it out. I wish we had nice abbreviations, right? Displacement. Ooh, who has the time? Okay, integral from a to b. They should have given me a and b. Here it is, the time interval. That's a, that's b. Fabulous. So we're going to integrate from 0 to 10, t squared plus 3t minus 4 dt. Okay, great. Here we go. So antiderivative of t squared. Add 1 to the exponent, divide by the new exponent. So that's going to be 1/3 t cubed plus 3/2 t squared minus 4t. All of this from 0 to 10 we're going to evaluate now. All right, 10 cubed, that's 1,000 over 3 plus 3/2 times 100 minus 40. And then if I plug in 0, everybody's 0. right, 1,000 over 3 plus, this is 300 over 2, which is 150. 150 minus 40 is 110, which ends up being 330 over 3, right? So 330 plus 1,000 is 1,330 over 3. Did they give me units? No. How rude. Pretend we're in meters. It just feels better. If there's no units, I would just put units, you know? But we're just going to make it a little more realistic. Meters. Just put M. We're good. Everyone should know. Okay, now it's going to get more spicy. Now we need the total distance traveled. Oh my. So total distance is going to be integral from 0 to 10 of absolute value of v of t dt. So what I want to know is, does v of t change signs, right, on the interval from 0 to 10? So in order to answer that question, I'm going to set the velocity function equal to 0 and see. So it factors. You're welcome. So t plus 4 times t minus 1 is 0. And we get t equals negative 4 and t equals 1. Now we're looking only on the interval from 0 to 10. So I'm going to throw away t equals negative 4. It's outside of this interval. But at t equals 1, the velocity is 0. So let me make a little sign chart. 0, here's 1, here's 10. And let's figure out the sign of the velocity function. So between 0 and 1, say you're testing with t equals 1/2, okay? If I plug in t equals 1/2 right here, that factor, 1/2 plus 4 is positive. 1/2 minus 1 is negative. So the velocity is negative in this interval. That means the particle is moving in the negative direction. And then pick somebody here from 1 to 10, say t equals 2. If I plug that into velocity, easiest place to plug in is just when it's factored. 2 plus 4, that's positive. 2 minus 1, that's positive. So velocity is moving in the positive direction from 1 to 10. So it kind of looks like this. T equals 0 to 1, it's moving this way. And then from 1 to 10, it's moving the other way. And since I want the total distance traveled, I don't want this little piece to get erased. So what we just found, the 1330 over 3, 1330 over 3, in part A, the displacement, that's the change. Oh no, that's not that, excuse me. From initial position to final position. So displacement's giving us this. That's the 1330 over 3. It's just looking at where it starts versus where it finishes. But this little moment basically gets erased in our answer for part A because it's moving in the negative direction, then the positive direction. But I don't want to lose it. I want total distance traveled, right? Pretend they're counting their steps. And you're like, oh man, just because I walked in circles, my step counter says 0. No, you got some good steps in here. We don't want to lose that. Okay, so that's what we're going to find here. So how to do it? Well, I know that this portion here is going to come out negative. I'm going to break up my integral. So instead of going from 0 to 10 all in one shot, I'm going to have to go 0 to 1 and then 1 to 10. All right? Allow me to show you. So total distance traveled is going to be integral from, 0 to 1 of v of t dt. Now in that interval, velocity is negative. So I'm going to add absolute value after. So that distance traveled doesn't cancel with the rest of what's going on. 1 to 10 v of t dt. Now I don't need to put absolute value on this integral because I already know velocity is moving in the positive direction, so it's going to come out positive. I don't know how particular your teacher is, but you can skip this whole part and just break it up and put absolute values on everybody. This one doesn't need it, but it doesn't hurt if you put it, right? If it's already positive, nothing bad is going to happen. You just have to know to break up the integral everywhere t equals 0. And then you're fine. Then you don't have to check, was it positive, was it negative? This one's going to be redundant, but I mean, you know, then you have less work to do. Okay. Anyways, we've done a lot of this already. So v of t, we had it up above, t squared plus 3t minus 4. I don't want to rewrite everything painstakingly, so I'm just already going to bust out the antiderivative. 1/3 t cubed plus 3/2 t squared minus 4t from 0 to 1, and then we're going to take absolute value after, plus, I'm going to leave them, but I know we don't need them, right? 1/3 t cubed plus 3/2 t squared minus 4t from 1 to 10. And then plugging everything in, let's see, this is going to be 1/3 plus 3/2 minus 4, and then minus 0 for the lower limit, plus, and then I already know if I plug in 10, the upper limit, because we did it earlier, it's 1330 over 3 minus 1/3 plus 3/2 minus 4. Okay. And then this is going to give me negative 13 over 6, but I'm going to take the absolute value. Do you see that? So crucial. Plus, and then here we have 1330 over 3. This is also negative 13 over 6, but minus negative 13 over 6 makes it plus 13 over 6. So then now this is positive 13 over 6 plus, this is going to be 2660 over 6 plus 13 over 6. So I have 2686 over 6, which is 1343 over 3. We decided we're in meters, didn't we? Okay, that's a house. So back to the little diagram I made. These 13 over 6s cancel out when we're doing displacement, because this negative and this positive would have canceled out. But so that means this way was negative 13 over 6. This is 13 over 6, but I want total distance traveled, so I'm adding an extra 26 over 6. That's it. There's not really much more to it. I hope this was helpful. That concludes the video. Give it a thumbs up. Subscribe if you haven't already. If you enjoyed all the Calculus 1 video lectures, guess what? I have them for Calc 2 and 3. And I'm working on linear and differential for members of the channel as well. If you want access to practice exams, more exclusive content and whatnot, you can join my Patreon. The link is in the description. Thank you guys so much for your support. Leave a comment down below. I hope your finals go well. I love you all. You can catch me on Instagram and TikTok too. Math TV with Professor V. Bye guys.